Welcome to part 7 of this series of presentations on drillstring and drilling dynamics. My name is Ben Jeffryes. I'm now retired, but I was formerly a scientific advisor with Schlumberger. This presentation is more standalone than the others. They would definitely help to have at least gone through all the previous fluid-related presentations first. The acoustics described in this presentation is directly applicable to understanding the propagation of sound from downhole to surface in fluid pressure pulse measurement while drilling systems. This is an outline of what you will learn. Firstly, an explanation of how to derive the necessary one-dimensional equations, followed by a discussion of the attenuation of fluid waves from both laminar and turbulent effects. Then a few slides on reflection and transmission beyond the effect of impedance changes, particularly those from pressure drops of various kinds. And finally, how over the long distances of well bores, the acoustics of the fluid in the pipe couple to the fluid in the annulus. Firstly, let's see how to integrate the equations to get from 3 dimensions to 1. This is an example of how to arrive at one-dimensional acoustic equations when the borehole radius is small compared to a wavelength, for the particular case of a non-viscous fluid in an axisymmetric annulus. These are the full partial differential equations describing the fluid and pressure dynamics. The fluid acceleration is proportional to the pressure gradient, and the rate of change of pressure is proportional to the divergence of the fluid velocity. We take the axial component of the first equation and simply integrate across the annulus to get equations for the mean fluid axial velocity and the mean pressure. For the second equation, we have to apply Stokes' theorem to get equations involving the same mean quantities as before, and also the radial fluid motion at the boundary. If there is a stiff inner boundary, for instance a rigid solid rod, then the radial velocity on the inner boundary is 0. If the outer boundary is a uniform elastic solid, then the outer boundary condition in general must be matched to an outgoing solution of the elastic wave equation, which involves Bessel functions. At low frequencies, though, it has this form for a uniform rock with a thin steel casing surrounding the annulus. If we approximate the pressure at the boundary by its mean value and include it into the rate of change of pressure equation, we find that fluid waves in the annulus are slowed down compared to having a rigid boundary, and there is an effective annulus bulk modulus, which is reduced due to the shear compliance of the rock. Having a steel casing significantly increases the rigidity of the borehole wall. Now, on to attenuation. The physics of viscous attenuation is quite straightforward. The viscous effects decay exponentially with distance away from a surface, and the decay length goes down with frequency. The shear stress on the wall depends on the inverse of the decay length, so this goes up with frequency. If you're looking at drag in a channel that is large compared to the decay length, then all the effect is localized at the wall, and the attenuation will grow proportionally as 1 over delta grows. However, if the channel width is less than delta, then the wall stresses look much more like a time-varying version of the steady-state solution, which I will term quasi-stationary. In some cases, we can solve the whole problem analytically and see when there is a crossover between the quasi-stationary and the properly dynamic solutions. If we look at steady viscous flow in a pipe and simply put in a time-varying flow, this is the equation that results for the wave number versus frequency. For ultra-low frequencies, the term linear in frequency dominates, and the wave number squared is proportional to I times the angular frequency. For viscous fluids in circular pipes, though, we could write down an exact solution in terms of Bessel functions, which is what you see written here. This defines k, the wave number, in terms of omega, the angular frequency. In our situation, this equation is more tractable than it appears at first sight. Although the two terms sigma and psi look quite similar, in SI units, the bulk modulus kappa is about 10 to the 9. The viscosity eta is less than 1. For the dimensions and frequencies of interest, sigma times the radius a is very small, so can be approximated by their values close to 0. J0 of sigma a is 1, and J1 of sigma a is sigma A over 2. Conversely, the equation for chi is dominated by the first term, and so depends only on frequency. Substituting into the equation for wave number, a surprisingly simple solution for k appears in terms of Bessel functions of a complex argument. The low frequency limit is, as expected, the quasi-stationary solution, which is comforting. At high frequencies, we could use the asymptotic expansion of Bessel functions to derive the following expression in powers of root frequency, where I've kept the first few terms. When the real part of the wave number is much bigger than the imaginary part, as is true for acoustic waves, we obtain a simple expression for the attenuation in powers of root frequency. The leading term grows as root frequency. Then there is a frequency-independent offset, and the other terms are small and decline as the frequency increases. If we plot the attenuation against a scaled root frequency, we obtain the graph on the left. The solid line is the exact solution, and the two dashed lines are the low frequency and high frequency limits. At very low frequencies, it is a straight line through the origin, as the attenuation is proportional to root frequency. At high frequencies, it is an offset straight line at a different gradient, as the attenuation is proportional to root frequency plus a small offset. The range of frequency for which neither the low nor high frequency limits is a good approximation is surprisingly small. So how does this dimensionless zeta correspond to actual frequencies? For water-based mud parameters, 10 centipoise viscosity, slightly denser than water, and 2-inch radius tube, zeta at 1 Hz is 2000. So square root zeta is 45, and we are way off the right-hand side of the graph. At a frequency of twice per hour, zeta is 1.1, and so the very low frequency limit is appropriate. It is not at all clear, however, how this applies to acoustic attenuation inside drill pipe while drilling, as the flow in the pipes is not laminar but highly turbulent. This has a much higher steady-state frictional pressure drop than for laminar flow. The low frequency limit of acoustic attenuation has to agree with a quasi-stationary turbulent solution, not a quasi-stationary laminar solution. With turbulent flow, there is an additional length scale to consider when looking at drag. There's the same two as before, the diameter of the pipe, or more generally the distance between outer and inner diameters, and the decay length for the viscous drag. But in addition, there is the thickness of the laminar layer of the contact surface. In turbulent flow, although the majority of the flow is undergoing high shear, at the solid boundary there is a thin layer which is still laminar. If the flow velocity changes, this laminar layer thickness will also not change instantaneously. If the viscous shear length is much bigger than the laminar layer, then we can look on flow variations as being quasi-stationary. At sufficiently high frequencies, if the laminar layer is much bigger than the decay length for the dynamic viscous drag, it seems reasonable to assume that the drag is the same as in the laminar case. At frequencies of around 10 Hz and above, the laminar attenuation formula fits field data reasonably well. In the intermediate situation, beyond the assumption that attenuation grows with frequency, it is difficult to know what to do. Let's try plotting the two limits as with the laminar case. Just as with the fully laminar case, we can plot high and low frequency approximations. The frequency and attenuation have again been non-dimensionalized. The line almost through the origin is the high frequency approximation. The line that asymptotes to a y-axis value of 20 is the turbulent quasi-stationary approximation. The real frequencies where the quasi-stationary solution predicts higher attenuation than the laminar solution depend on the flow rate and viscosity. But for high viscosity drilling fluids will be around 1 to 2 Hz, lower for lower viscosity fluids. It seems reasonable to assume that the actual attenuation keeps on rising and does not level off like the quasi-stationary solution. The solid line is a possible approximate exponential transition between the two, but is really a guess. It would be nice to have some real data to go on here, but experiments are problematic to perform with the right parameters. From something where we aren't sure what to do between high and low frequency limits to a subject that is a bit easier to calculate: reflection and transmission of acoustic waves. This is what you normally learn about reflection and transmission in one-dimensional acoustics. It's all about impedance. For fluid, that means area changes. Match pressures, match volume flow, and that gives formulae for reflection and transmission. The formula is antisymmetric. The reflection coefficient changes sign depending on the direction the wave comes from. And there's no dependence on the mean flow. It's completely linear, and it's energy conserving. However, there's something else that generates reflections in pipe with mean flow, and that's orifices, or similar pressure drops. It's non-linear, so there is a dependence on mean flow rate, but we can linearize, and similarly match pressures and volume flow. Here, I'm assuming that the area is the same on both sides of the orifice. We can calculate reflection and transmission like before. It looks quite different though. Firstly, the reflection is symmetric, the same reflection coefficient from upstream or downstream. Also, it varies with mean flow. The higher the flow, the bigger the reflection, and also it is lossy. The whole reflection process dissipates acoustic energy. Somewhere there is a big pressure drop and an area change is at the bit. The annular cross-sectional area is bigger than that of the fluid inside the pipe. But in addition, due to the reduced effective bulk modulus in the annulus, the impedance is further reduced. When there is a combination of an impedance contrast and a pressure drop, the reflection coefficient can change sign as the flow rate increases, which often happens with drill bit nozzles. At sufficiently low flow rates, the reflection of acoustic waves is positive with respect to flow variation, negative with respect to pressure variation. It is similar to a free surface. As the flow rate increases, the nozzles act more and more as a barrier to flow variation, and the boundary looks more and more like a fixed end. So a negative reflector for flow variation, positive for pressure variation. This is a significant issue for acoustic sources, such as measurement while drilling systems, MWD, located above the bit. They are dipole sources, and so generate both an upgoing wave and a downgoing wave of the opposite sign that travels down towards the bit, from which it is reflected. And depending on the phase shift and the sign of the reflection, this can interfere constructively or destructively with the direct upgoing wave. There can be circumstances where a change in flow rate alters constructive to destructive interference, significantly reducing the apparent signal strength. Something else with a pressure drop that sound may have to get through in a drill string is a motor. There are a number of occasions when MWD sources are placed below motors. In casing drilling assemblies there is no option, but also when running rotary steerable systems below motors, the MWD system may also be placed below the motor to get the surveying measurements close to the bit. What happens to the signal in these circumstances? It's not immediately obvious why the motor should reflect low-frequency sound. To get a reflection, there has to be some relationship between pressure drop and flow rate, and the pressure drop across a motor depends on the torque applied to it, not the flow rate. But there is a dependence when there is a lot of mass being turned by the motor. The motor needs to supply torque not just to turn the bit, but also the collars below the motor. And while turning them at a steady speed always requires the same torque, increasing or decreasing the rotary speed requires a change in torque. Since the rotary speed is proportional to the flow rate, this is the pressure-flow rate coupling. Torque proportional to rate of change of rotation speed becomes pressure proportional to rate of change of flow rate, and we end up with our old friend, the one-pole low-pass filter. So for low-frequency sound, positive displacement motors act as a one-pole low-pass filter. Crucial for real-world acoustic transmission is the filter frequency, and for typical motors and BHA sizes, it will be over 10 Hz, so for normal MWD systems it has little effect. Higher frequencies, though, can be significantly attenuated. Final acoustic subject: the coupling of pressure variations in the pipe to those in the annulus. This is the situation we will be modelling. A fluid-filled borehole, radius capital D, with a constant cross-section drill pipe in it, inner radius A, outer radius B. The pipe is central in the borehole, which, while making calculations tractable, is not realistic. I don't think, though, at the frequencies where the 1D approximation is a good one, it makes much difference. Outside the borehole is a casing of thickness H and a rock with shear modulus mu. This results in a lower effective bulk modulus for the fluid in the annulus than for the fluid in the pipe. We can go through the same 3D to 1D integration process as I described at the beginning of this presentation for the whole system, and end up with a set of coupled equations for the fluid inside the pipe, the fluid inside the annulus, and the axial motion of the steel. I have written them here in terms of pressure for the fluid and axial motion for the steel. They are fully coupled. There are no zeros in the matrix. The diagonal terms look like wave equations. The off-diagonal ones are coupling and involve both frequencies and wave numbers. The terms that couple metal and fluid all include the Poisson's ratio of the steel. The proportional amount that a solid moves perpendicularly to the direction of propagation of a compressional wave. The terms in the top right and bottom left, coupling inner and outer pressure, are due to the radial compliance of the pipe. If you set the determinant of this matrix to 0, a cubic equation in the wave number over frequency squared results. So there are 3 sets of waves in this system, moving at speeds which do not depend on frequency. One is very largely a steel wave, the other 2 largely fluid. This uses a static approximation for the surrounding rock, which is not bad if the borehole radius is much smaller than the wavelength for shear waves in the rock, but shear waves can be quite slow. If the waves in the borehole are faster than either the shear or compressional wave speeds in the rock, there will be some attenuation due to the generation of outgoing elastic waves in the rock. The effective bulk modulus of the annulus can be written down in a form which takes full account of the properties of the rock, which is shown here, where CS and CP denote the shear and compressional wave speed of the rock. These expressions are for the case with no casing. They are more complicated when casing is present, but the problem is still tractable. To find the zeros of the determinant, numerical methods must be used. Waves in the steel, which are generally faster than both shear and compressional waves in the rock, do generate radiation, and hence are attenuated, but only very slightly. Fluid waves in the annulus that are faster than the shear wave speed in the rock could generate significant radiation, but since a low shear modulus also slows the waves in the annulus, a fluid wave speed significantly higher than the shear wave speed in the rock seems difficult to achieve. However, if a layer of casing is introduced, then the annulus appears a lot stiffer to the fluid and hence increases the wave speed, but the rock is still slow, and appreciable radiation loss can occur at frequencies of around 100 Hz and above. Going back to the low frequency approximation for a moment, since the steel waves have a much lower wave number than the fluid waves, it is not a bad approximation to take the limit as the steel axial sound speed tends to infinity, so that the second row of the matrix is now proportional to k squared, and then the axial velocity in the first and third equations can be replaced by the appropriate linear combination of inner and outer pressures. Having done so, this results in the following pair of equations, which have 2 solutions. For the faster of the 2 solutions, the 2 pressures, inner and annular, are in phase. For the slower solution, they are out of phase. Let's look at what the solutions look like for different situations. This is the wave speeds for a very stiff borehole, in fact one that has been drilled in steel, with the speed plotted against a ratio that reflects the annular shape. At the left, there is a vanishingly small pipe. At the right, the annulus is vanishingly thin. The fast wave speed barely varies over the whole annular size range. In contrast, the slow wave speed drops considerably for a very thin annulus. This is a close-up of the fast wave speed. It varies by about 1% in total. I've said that for the fast mode, the inner and outer pressures are in phase, but what are their relative sizes? They are a bit different, more inside the pipe than out, and while they vary more than the fast wave speed, they don't vary hugely. In contrast, for the slow wave, where the pressures are out of phase, they vary enormously, from being almost completely inside the pipe for a tiny pipe, to being almost completely in the annulus for a tiny annulus. That was a rather unphysical situation, an annulus with the shear modulus of steel, though some limestones and igneous rocks can be close. What about when the annulus is a relatively soft rock, the shear modulus of a soft shale? Due to the effect of the radial compliance of the borehole, while the fast wave is not much different to that in the stiff formation, the slow wave is much slower. The ratio of the pressures for the fast wave is very different. Over most of the annulus size range, almost all of the pressure is inside the pipe, with only a significant amount in the annulus for a thin annulus. The ratios for the slow wave are reversed, almost entirely in the annulus for the whole annulus size range. It seems clear that there is less mixing of sound inside and outside the pipe when the borehole is soft than stiff, but it is worth looking at some examples on what happens when there is a sound source in the pipe. Let's take a 1-cycle 10 Hz pulse inside 5-inch pipe in an 8-inch annulus in a soft formation. This is at the source. There is no viscous drag in these calculations, which will add attenuation. Now let's look 500 meters up the borehole. There is a small tail to the main wave. This is the slow wave. The annulus pressure is plotted in red and is small. The same at 1000 to 2000 meters. The fast and slow waves have separated due to their significantly different wave speeds, but there is never very much pressure in the annulus. Same pulse, but now for a stiff annulus. After 500 meters, a significant proportion of the pressure has shifted to the annulus. There are fast and slow waves, but they are close together in speed, and there is little separation. By 2000 meters, the two propagation modes have separated out a bit. The proportions in the pipe and annulus have reached their equilibrium levels after about 500 meters, so there is no further shift. Now you may think this has little relevance, but cased boreholes and drilling risers can be very stiff, and so over long distances there can be significant proportion of the acoustic signal from the MWD in the annulus. Not as people normally assume because it has come through the bit, but through the compliance of the pipe. Now let's do a similar calculation for a similar pulse at a lower frequency, 2 Hz. The leakage of energy into the annulus takes place over a much longer distance. It has not reached equilibrium by 2000 meters. That is because the distance over which the pressure shifts is inversely proportional to the frequency. With a 2 Hz pulse, it takes about 3000 meters to equilibrate. Finally, a summary. For fluid waves in a pipe in a borehole, there are always two modes. A fast mode with the fluid motion and pressures in phase, and a slow mode with them out of phase. For a hole in a slow formation, there is a large difference between the two mode speeds. The fast mode is largely in the pipe, and the slow mode largely in the annulus. For a source inside the pipe, the distance over which some pressure migrates to the annulus is quite short. For a hole in a hard formation, or cased hole, there is a much smaller difference between the mode speeds. The relative proportions of pressure in the pipe and annulus are quite similar, though there is more fast in the pipe and more slow in the annulus. However, the distance over which the pressure migrates to the annulus is much longer. That's the end of this presentation on acoustic topics, which is the last one looking at the long-distance propagating dynamical modes, namely axial, rotation, and fluid acoustics. The final 3 presentations are all about bending and lateral dynamics, and we'll start with pure bending statics. Bending has additional degrees of freedom and also depends on compression and hole angle, so there is plenty to cover. Questions, comments? Please direct to the email address at the lower right.